Hello and welcome to lecture 61 of the course Computational Complexity. So in the past couple of lectures we have been seeing the power of interaction, right? So instead of getting a static proof from a prover, what more could we accomplish if we were able to interact with the prover, right? And we saw graph non-isomorphism. We saw that it had an interactive proof. But the proof crucially used the fact that the random coins were withheld from the prover. We also saw the proof for sharp 3 SAT in interactive proof for sharp 3 SAT, where in fact all the randomness was made open to the prover. Right? So we want that which was a public coin protocol, the randomness being revealed to the prover. So we want to understand what is the power when the randomness has to be made public or randomness has to be announced to the prover. So it is okay to think of it as a restriction, because an interactive proof does not by itself require the randomness to be made open to the prover. But if you make it open to the prover, perhaps you cannot do some things that you could have otherwise done, right? Like we did in the case of graph non-isomorphism, right? So with this restriction of having to compulsorily announce to the prover the random coins, what could we achieve, right? So this is what we will see in this lecture. So this is public coin interactive proofs, and this is commonly known as Arthru-Merlin proofs. Okay, so Arthur stands for King Arthur, who had a wizard called Merlin in his court. Right, and so Merlin is like this wizard, so he knew he is all powerful. He even knew what Arthur may possibly ask, right? So, and just like the prover being all powerful, and this terminology Arthur-Merlin will be used only in the case of public coin proofs. Okay, so we may we may think of the interactive proofs or the public coin interactive proofs or the Arthur-Merlin proofs as one where the verifier has to compulsorily announce the random coins, right? So let us say we enforce this. So what did we have in the first model? We had verifier sending a message Q1, right? Over here we have Q1 and the prover sending A1 as in response. And the Q1 is a function of the input X and the random coins generated for the first round, say R1, right? So this is function of X and let's say R1, because I am just writing F. So now what is the need for the verifier to compute Q1 and send? So suppose the verifier also sends R1 along with Q1. There is no real need for the verifier to compute F, because the prover can himself compute F, right? So all the prover needs is R1, which is generated at the verifier's end. But by the model here, the verifier is forced to send R1. So all the verifier needs to do is send R1, because X is also known to the prover, and once the verifier sends R1, the prover also knows R1, and the prover may as well compute F and then sends the response. And similarly in round 2 maybe, or round then sends the response, and then instead of Q2 again the verifier may just send R2, the next set of random bits that he has generated. So the point here is that there is nothing lost by restricting the prover or restricting the verifier to only send the random coins, because any function that he intended to compute could be computed by the prover himself. So in this model the verifier will only be sending the random coins. Okay, the prover is called so just as I said before, the prover is called Merlin and the verifier is called Arthur. Okay, so this is, as I said, it's equivalent to the model where verifier only sends the random coins. Okay, so we will restrict the verifier to only send random coins, but this is equivalent to the situation where the verifier sends queries and random coins, because prover can anyway compute the queries. And the key thing is that the random coins are revealed only as they are generated. So if you think of the sharp 3 SAT proof, right? The prover was sending, the verifier was sending the random coins, but if the verifier sent all the randomness right at the beginning, right? So let's say the verifier generated all the randomness right at the beginning and sent to the prover, then the prover could possibly cheat by looking at the entire set of random coins and then engineering a function at each step, right? So because he knows that what is going to come in the future. But what really helped was the fact that every randomness was generated at the time, so the prover does not know what to expect in the future, and this was used, right? So just like that, we will insist that the random coins are revealed as and when they are chosen. So the verifier will require randomness for a particular round, he will generate it and then send it. So the prover does not know what random coins are going to be generated in the future, okay, they are not known upfront. So the class AM is stands for Arthur-Merlin proofs, and AM without qualifying the number of rounds stands for AM with 2 rounds. Okay, so meaning AM, Arthur speaks first, the verifier speaks first, and then Merlin speaks. So Arthur sends the randomness R, okay, and verifier and the prover sends the message M. Okay, the Merlin sends the message M. So AM stands for AM with 2 rounds. Okay, so this is a bit inconsistent with what we said for IP. We said that when we do not qualify the number of rounds for IP, it stands for polynomial many rounds. But in the case of AM, it stands for just 2 rounds. So let's try to look at the completeness and soundness. So when X is in the language, completeness, a random string is sent, and the prover, if X is in the language, prover should be able to pick a message such that the verifier should be able to verify the message R, the message M, the random string R, and his input X, and it should be accepted with probability at least 2/3. So A is the function of at the verifier sent, capital A. R is the random coins, X is the input, M is the message from the prover. So if X is in the language, prover should be able to pick out a message M such that the probability of it getting accepted is, or rather, the R is already chosen. So for 2/3 of the choices of R, at least 2/3 of the choices of R, the verifier, the prover should be able to pick out an M. Right? So in some cases there may not exist a M, but that's okay for as long as majority of the cases or 2/3 of the cases, the prover can pick out an M. And the soundness, when X is not in L, for the majority of cases, for 2/3 of the cases, the prover should not be able to pick out such an M, or in fact, the probability that the prover can pick out an M that leads to acceptance is at most 1/3. Okay, so notice that we have the existential quantifier for the soundness also. This is not a typo, it is the existential quantifier because verifier sends the randomness and the prover, what is the probability that the prover can pick out a message M that leads to acceptance, right? So this is the same in the case of sound completeness and soundness. This is the only case where AM is the only case where we will be having this, there exists in both cases, right? So just a pictorial depiction of the protocol here. Arthur sends a random string, M sends a message, and then it is checked. So similarly, like AM, we could define a class called MA, and MA is also MA with 2 rounds. When we do not qualify how many rounds it is, MA is also MA with 2 rounds, right? And this happens, so as you may guess, MA stands for Merlin sends the message first. Okay, so I have drawn it here. Arthur generates, and then Arthur generates the random string and then verifies. Okay, and this random string Arthur could possibly send it to Merlin, but then there is nothing to be accomplished by sending it to Merlin, right? Because there is nothing more to be heard from Merlin. So it is just, so in fact MA of 2 is just one round of communication, but the second round Arthur generates R, the random bits, and then does the verification. So Merlin sends the message, Arthur generates the randomness and verifies. So completeness, when X is in the language, there should exist a message M that the prover can send, such that for most random coins picked out by the verifier should lead to acceptance. And soundness, when X is not in the language, whatever for whatever a message picked out by the prover is not going to be accepted beyond a probability 1/3. The completeness, there should be a message with prover that is accepted with probability at least 2/3. Soundness, whatever message is chosen by the prover, it is accepted with probability at most at most 1/3. Okay. So here we have again there exists and for all. So MA also without qualifiers indicates MA with 2 rounds, which is what I described just now. And it is convenient to think of MA as just like NP, where everything is like NP, where so it's just like Merlin sends a message or a certificate that needs to be verified. Just that the verifier machine is a probabilistic machine, right? So instead of a deterministic machine, it's a randomized machine. So like in the case of interactive proofs, we can assume that it is perfect completeness, or we can get perfect completeness, meaning the 2/3 can be pushed to exactly equal to 1. It can also be shown, so this we will not prove, in this course, we won't prove this, although it's not that difficult to show. So constant round public coin interactive proofs, right? Constant round public coin interactive proofs are either MA or AM. So if you had more rounds, let's say AM with a constant number of rounds, where AM with k rounds, this can be reduced to AM with 2 rounds, which is equal to AM, right? So this can be reduced to AM with 2 rounds, which is the same as AM. And even if you start with MA, so you can think of, so there are proof systems that is denoted MAM, meaning Merlin sends a message, Arthur generates a random bit, then again Merlin sends a message, or MA, like all of this will reduce to AM, right? The other thing that can happen with constant round interactive proofs, public coin interactive proofs, is that we just have MA, right? Which is just 2 rounds, Merlin sends and Arthur verifies. So the point here is that constant round public coin interactive proof systems, there are only 2 classes, MA or AM, both with 2 rounds, what we just described above. So in fact, it may be worth to just notice the contrast between the completeness and soundness of MA and AM just now. So in the case of AM, we have the probability is outside, there exists quantifier inside in both cases, 2/3, 1/3. In the case of MA, the quantifier is outside and probability is inside, right? Because the order of communicating is different, right? The order of communicating is different because in the case of Merlin Arthur, the Merlin chooses first and then Arthur has to respond with randomness. And in fact, there is a way to denote this also. So in the case of Arthur-Merlin proofs, so it's like Arthur sends random coins, and then Merlin has to like existential quantifier for Merlin, right? And then again Arthur has to send some random coins and so on. Right? So you can view it as a tree. So in fact, Arora has this picture that you can have a look. So Arthur will send a random coin each round, and Merlin has to pick out. It's like an existential quantifier. So it is kind of like AM is like a member of the polynomial hierarchy, where instead of the for all quantifier, we have the random probability thing. Okay. And once again, constant k boils down to either AM or MA. So in fact, this proof we will highlight. We will see the proof AM k is equal to AM. Okay. So we saw AM, we saw MA, both being public coin protocols, and we will see that MA. We will see now that MA is contained in AM. You may guess that this is indeed the case, or rather it's intuitive to guess that this is indeed the case, because in the case of MA, the prover has to pick out a message before seeing the randomness. In the case of MA, he gets to see the randomness and then pick out the message. So the prover has more information in the case of AM, right, and presumably he can convince more things with that information. So MA is actually contained in AM. So when the prover is not able to see the randomness, or when the prover is able to see the randomness early, he can do whatever he could do even otherwise when he did not see the randomness. So let us see the proof of this, right? MA is contained in AM. Suppose, so as always, we pick out L, an arbitrary language in MA, and we will show that it is contained in AM. So L is in MA, which means L has an MA proof system. We will see how to modify this to get an AM proof. So the completeness and soundness for the MA proof system is that X is in L, then there X is a message that Merlin should send, such that the probability of accepting the message is at least 2/3. Soundness means X is not in L. For any message that is being sent by Merlin, the probability that Arthur accepts it is at most 1/3. And we can amplify this 2/3, 1/3. So we already said we can attain perfect completeness, but just like what we did in BPP, we could amplify it to extremely close to 1 and extremely close to 0. So 1 minus 1 divided by 2 power L plus 1 and 1 divided by 2 power L plus 1, where L is chosen to be the length of the message sent by Merlin. Okay, so this will come a bit later. I'll highlight it again, why we chose this probability. So let us see completeness. Okay. So we have this, when X is in the language, suppose X is in the language, this means there exists an M such that probability of acceptance is at least 2/3. So now let us try to draw this matrix as I have in the right side, where rows are indexed by random coins and columns are indexed by messages that are sent by Merlin. So what does it say? It says that there is a column that has a big fraction of ones, right? Because the completeness is there exists M such that the probability of acceptance is higher. We said it is 2/3, but then we said we are going to boost it to 1 minus 1 divided by 2 power L plus 1. So this means there is a column, such that this column has 1 minus 1 by 2 power L plus 1 fraction of ones. So which means a large fraction of entries in this column are ones. Right? So maybe I'll just highlight this. This column, a large fraction are ones. Now let us look at the completeness condition of AM. Okay, so where the randomness is sent, and then so for which values of R can Merlin pick out a message that will lead to acceptance, right? And so let's say this. So before that, let us say this column which had at least this many ones. Let us call this column M star. Okay, which is what I have written here. So the point is that now if we choose the randomness first, now Merlin has to pick out some message that will lead to acceptance. So Merlin already knows the randomness, right? So the question is, once he chooses the randomness, will Merlin be able to pick out MM? So we know that already in this column a huge fraction are ones. So which means that if for these entries, these rows where this column has ones, as long as a column has any one, as long as a row has any one, that random choice of R is good. But already we know that a majority of random the choices of R are good because there is one column that has a huge number of ones. So in fact the same M star will work for most of the for almost any R, right? So the same M star Merlin does not even need to think. The Merlin could just send M star and that will work for almost all of the R's, because M star itself works for a huge fraction of the inputs. So that is the completeness. So the problem, you can take the existential quantifier inside the probability. So in other words, we are saying that the completeness condition for AM happens to be implied by the completeness condition for MA. Okay. And now let us see the soundness. The soundness is a bit more involved, only slightly more involved. So soundness condition for MA is that for all M, suppose X is not in L, right? Suppose X is not in L, right? Then for all M, the probability that it gets accepted is at most 1 by 2 power L plus 1. So let us see pictorially what this means. We again have the same matrix M and R. So now as you can see, there are more zeros than ones because X is not in L, so the probability of acceptance is at most 1 by 2 power L plus 1. This means that for each column, the number of ones is at most, each column number of ones is at most 1 by 2 power L plus 1 multiplied by number of rows. Okay, because we know that the probability is at most this. So what is the total number of ones in the matrix? So each column has this many ones. So this is equal to total number of ones is at most this quantity, which is 1 by 2 power L plus 1 into number of rows multiplied by number of rows multiplied by number of columns. But how many columns are there? So remember, we said that the length of message that Merlin sends is equal to L, and assuming 0 1, I have been assuming 0 1, although I didn't make it explicit. This means the number of columns is actually equal to 2 power L. So this means that this is equal to the 2 power, so it's like 2 power L divided by 2 power L plus 1 into number of rows. So which is half multiplied by number of rows. So the total number of ones is at most half times the number of rows, right? This means that the total number of ones in this matrix is at most half times the number of rows, which means that the number of ones is itself half the number of rows, which means at least half rows are all zeros, right? Because the best you can distribute the ones is you can put exactly 1 1 in each of the row, but you only have so many ones. Let's say this matrix has 100 rows, you only have 50 ones, so you can put each one for the first 50 rows and the remaining 50 rows do not have any ones. So which means for half the rows there are no ones at all. So the half the rows are all zeros, at least half the rows, right? So this means that this means that what is the probability? So if the random choice of R is for those half where there is no, which correspond to all 0 rows, then Merlin will not be able to send out an M because all those rows are entirely zeros. So with probability at least half or at most half, or with probability at most half, with probability at least half, Merlin has no choice, no way to convince a verifier, which means the probability of acceptance is going to be at most half. So the same thing again here in a different way in the left side. So what is the probability? So this is the soundness condition for AM. What is the probability that there exists an M that leads to acceptance? So this is like the worst case is this is a union, and you can take the union bound. So you can take the summation of all the probabilities, summation over all M, the probability that M will lead to acceptance, and the probability that a specific M leads to acceptance is for the probability that for a specific M and the R gets accepted is at most 1 by 2 power L plus 1 by the soundness condition above, and you sum it over all M, you get half. which is exactly the same computation that we did over here. This we got this 2 power L divided by 2 power L plus 1. So it's exactly the same proof, but here it is more mathematical notation, and the right side I try to present it in a different way, by looking at the matrix. So which means for with half probability, for half the choices of R, at least half the choices of R will lead to all 0 rows, and Merlin will have nothing to respond to that could lead to an acceptance. This means with the probability of acceptance is at most half, right? So this is why we needed to boost, because we use the union bound, right? So the soundness is at most half, and the completeness is at least 1 minus 1 by 2 power L plus 1. So there is a gap here, right? And so you may think that this is not less than 1/3, but then I could have chosen the amplification to 1 divided by 2 power L plus 2. So in which case I would have got 1/4, which is not really a big deal, right? So that completes the proof that MA is contained in AM. So which means if you have by revealing the randomness to the prover, you potentially are able to the prover can convince more things to the verifier. So MA is contained in AM, and we can also, it's not that difficult to see that we can, whenever MA shows up as a part of a protocol, we can replace it by AM, and this is the proof that any constant round protocol can be reduced to a 2-round protocol. So if you have an AMA protocol, right, AMA protocol, this can be reduced to, so this MA can be replaced by AM, and it can be replaced by a AAM protocol, and AAM means it's like 2 sets of random bits sent by Arthur. So instead you can think of it as 1 set of random bits and send it in one go. So that's actually AM. And similarly, even if you have MAM, where Merlin, Arthur, Merlin, so in the first case, this AM was replaced by, in the first case this MA was replaced by this AM. In the second case, this MA can be replaced by this AM, and instead of Merlin sending two M1 and M2, 2 strings one by one, instead of that you can think of him as him sending a big string M1, M2, concatenated or something. So even that is equal to AM, and you can do this as long as it's a constant number of such replacement operations. That's why whenever we have constant many rounds, this can be replaced by a 2-round protocol. So either AM2 or MA. Okay. So MA is not is only at most as powerful as AM, and we have this proof that constant round protocols are either AM or MA. Another thing to note is that MA is contained in sigma 2, okay, which is a complexity class that does not have anything to do with interaction, because Arthur is a BPP machine, right? Arthur is does random coin tosses and then does some verification. So this BPP machine can be thought of as this BPP machine can be, Arthur is a BPP machine which is contained in sigma 2, right? And sigma 2 means it's a there exists quantifier, there exists for all quantifier, but Merlin is also a there exists quantifier, right? He has to send for completeness, he has to send, or rather we are testing whether he can produce a M that leads to acceptance. So this there exists for all, you can merge the there exists quantifiers to get a sigma 2. And similarly, BPP is also contained in pi 2. So when Arthur goes first, AM, this can be replaced by for all there exists, and for all there exists can be converted into for all there exists. So AM is contained in pi 2. So MA and AM are in sigma 2 and pi 2 respectively. Yeah, we know that MA is contained in AM. Okay. Okay. So now let's the final thing of this lecture is this is something that we had referred to when we talked about graph isomorphism. We had stated graph isomorphism as a candidate language that is NP intermediate. We said that graph isomorphism, we do not know of any polynomial time algorithm, nor do we think that it is NP complete. So this, I think, was lecture 22 or 23 when we talked about Leibniz's theorem, which discussed NP intermediate languages, right? So, so it is, as of now we do not know whether it is in P or if it is in P complete. The best algorithm is like a quasi polynomial time algorithm. Quasi polynomial meaning order 2 power log n to some constant. This is the this algorithm was by Babai maybe 3-4 years back for graph isomorphism. So we still don't know whether it is polynomial time. At the same time, it is unlikely to be NP complete. It is believed to be not NP complete, and we will see the reason why it is not NP complete in this theorem. So what this theorem states is that if graph isomorphism was NP complete, then sigma 2 will be equal to pi 2, which means the entire polynomial hierarchy will collapse to sigma 2. And as I would have said when talking about polynomial hierarchy, it is believed that the polynomial hierarchy is strict. So this theorem can be viewed as an evidence that graph isomorphism is unlikely to be NP complete. Okay, so let us see the proof. The proof is not very difficult to see. So since sigma 2 and pi 2 are sort of complement classes, it is, in order to show that sigma 2 is equal to pi 2, it is enough to show that sigma 2 is contained in pi 2. Okay, because we have seen this trick in many other proofs like NL equal to co-NL, for instance. So we will, assuming that graph isomorphism is NP complete, we will show that sigma 2 is contained in pi 2. Okay. By assumption graph isomorphism is NP complete, which implies that graph non-isomorphism is co-NP complete. This implies graph non-isomorphism is co-NP complete. This implies that any language in co-NP reduces to graph non-isomorphism. Right? So which means given a formula phi, right? So this is tautology. What is the so what do we have here? We on the left hand side we have the statement that for all y, phi y is true. So I put a bar about y to denote that it is a vector. So for all y, phi y is true. This is the tautology problem, which is this is the co-NP complete problem, and this can be we can reduce it to a graph non-isomorphism instance, because graph non-isomorphism by assumption is co-NP complete, right? So right, by assumption graph isomorphism is NP complete, which implies the graph non-isomorphism is co-NP complete, such that given a formula phi, we can construct a graph non-isomorphism instance Fi such that phi is a tautology yes instance for tautology if and only if Fi is a yes instance of graph non-isomorphism. Right? This is just the definition of what it means for graph non-isomorphism to be co-NP complete. So now let us take an arbitrary language in sigma 2p. Okay. So let us take a formula psi which is of this form. There exists x such that for all y, phi of xy is true. Right? This is a canonical sigma 2 sat formula. So now let us see, look at this, the second part, for all y, phi of xy. This looks like a tautology instance. Once for a fixed x, right? This is a tautology instance. So now I can write it this as a I can compute the reduction for this instance. So assume we fix x. So let us say we get f of phi x and with the variable y. Let's say we call it gx. So which means this will be a graph that depends only on the string x. because this formula phi depends on x, right? And the variable was simply y, right? So x was fixed. So we get with the same reduction above, we get a graph non-isomorphism instance called gx. So now that we have replaced this part, I'll maybe put a red bracket around this part with gx. Let us try to see what happens. So maybe I'll make this one also red. Right. So we are saying that psi is equivalent to, there exists x such that gx is a S instance of, or gx is in GNI, graph non-isomorphism, right? Because I can replace this for all y etc. with gx. And what we have seen, so far it is just restatement of sorts, right? So we have not even gone to interactive proofs. We are just talking about sigma 2 is contained in pi 2 and graph isomorphism and so on, right? We are just rewriting stuff. And here is what we have learned comes into play, what we have learned in interactive proofs, right? Graph non-isomorphism, we have seen that it has a 2-round Arthur-Merlin protocol, right, with perfect completeness, and soundness error is 1 divided by 2 power n plus 1. Right. So we can reduce soundness to as much as possible, the soundness error to 1 divided by 2 power n plus 1, and we also mentioned that perfect completeness can be accomplished. So I say not, maybe I'll say not proved, but not proved in class. I mean the perfect completeness. Soundness also, it is exactly similar to BPP amplification, right? So let us rewrite this in another way. GNI, so this is all that we have known to us, but let us rewrite this in another way. So this is I, what we have here is psi. Maybe I'll just put a red box around this as well. And this, so psi is true if and only if there is a claim here that for all random choices R, there exists x and m, there exists m such that a r gx of m equal to 1. Okay, where I'm just where a r gx m, this a is part of the Arthur-Merlin protocol for graph non-isomorphism. Okay, so this is from the Arthur-Merlin protocol for graph non-isomorphism. So let us see why this is true. Right? So we want to say that given this psi, let's say 1, we want to say that that is true if and only if this is true. So 1 and 2 are kind of equivalent. So let us do it in two parts. 1 implies 2 first. Suppose psi is true, right? Now we have perfect completeness for graph non-isomorphism, which means whenever gx is in GNI, the probability that the AM proof accepts is equal to 1, right? So the probability that Merlin can send a M is equal to 1. So what is psi here? There exists x such that gx is GNI. So if we rewrite, there exists x such that the gx is equal to GNI. We can again write it as there exists x such that this is true. And now, like we did earlier, so if there exists x such that this is true, we can even take the x inside. The choice of x, same x will work even if it is taken inside. So we can take x inside. So the probability that there exists m, there exists x, there exists m, this is true, is equal to 1. Which means for all r, there exists x and there exists m such that this is true, which is what we stated here in this box 2. For all r, there exists m and there exists x for which this is true. Right. Now the other direction, 2 implies 1. Right. Suppose there is a this is true that for all r, there exists x and m such that a r gx m equal to 1. Right. Or in fact, we will assume the opposite. We are not going to prove 2 implies 1. Rather, we are going to say that not 1 implies not 2. Suppose psi is not true, which means for all for all x, gx is not in graph non-isomorphism. Right? For all x, gx is not in graph non-isomorphism. For all x, gx is not in graph non-isomorphism. Now soundness tells us, right, we assume that soundness can be reduced to 1 by 2 power n plus 1. The probability that there exists an m, right, since gx is not a S instance, such that a or gxm can be accepted is at most 1 by 2 power n plus 1. This is exactly the soundness condition, right, for AM protocol. Now, much like we did over here, right, we did a matrix and we counted the number of accepts, rejects, zeros and ones. Much like that, so let us see. So this is R and this is M. So there is a matrix of zeros and ones and so on, right? And we know that so for any x, right, for any x, because for all x quantifier, there are at most 1 divided by 2 power n plus 1 r's for which there is a message m that leads to gx getting accepted. Okay, so this one indicates the acceptance of gx for that r and that m. So for any x, there are at most 2 power n plus 1 r's for which there is a message m. So what I want to say is that there are at most 2 power n plus 1 r's that have at least one in its row, right? Right. So there are at least one in its row. So for each x, right? That means, so now consider this is for a specific x. Now consider now another x and another x. So for each x there are some r's that are good. So which means for each x there are 1 by 2 power n plus 1 rows that are good. So what are the rows that are good for some x? So each row, the best possible is that all the rows are spread out and there are 2 power n multiplied by 2 power n divided by 2 power n plus 1 rows, which will be good for, or fraction rows that will be good for some x, which means that is at most half the rows, which means there are at least half the rows which will not be good for any x, right? So these r's will, any choice of m and x will lead to rejection, or rather no choice of m and x will lead to rejection. So there are r's. So I don't even need half the r's. That all I need is there are rows which will not be accepted for any x and any m. So there exists r such that for all x and for all m, a of r x gx m is not accepted, and which is the negation of what I have written in box 2. For all r there exists there exists r such that for all x and for all m, a r gx m is equal to 0, which is what we have shown. So so which means this is an equivalent restatement of psi. So psi was, to begin with, psi was a sigma 2, an arbitrary language or arbitrary thing to check from sigma 2, and now we have this equivalent characterization box 2 for psi. So notice what we have here. So A is a deterministic polynomial time machine, right? So the randomness comes from R. Once R is fixed, A is deterministic, and R is some input, X is some input, M is some other input, and we have this for all there exists quantifier. So these two quantifiers existential quantifiers for x and m can be merged. So it is just like a for all r there exists x comma m, this is true. So this is exactly how a Pi2 language should look like. So statement of the claim or the two statement gives a Pi2 characterization for L. So we started with the sigma 2 language L, and we have now shown a Pi2 characterization, which means sigma 2 is contained in Pi2. And the only assumption that we made was that graph isomorphism was NP complete, right? So this implies that graph isomorphism is NP complete, implies that sigma 2 is equal to Pi2, which means polynomial hierarchy collapses down to the second level. And this is an evidence, or this is an indication that, because we believe it will not collapse to the second level, or we will not collapse at all, we feel that graph isomorphism is unlikely to be NP complete. Is unlikely to be NP complete. And that is all that I have for you in this lecture. So just to summarize, we saw Arthur-Merlin public coin interactive proofs. We called it Arthur-Merlin proofs. Arthur is a verifier, Merlin is a prover. We saw the characterizations for two-round protocols AM and MA, or two-round proof systems AM and MA. So AM stands for AM with 2 rounds, MA stands for MA with 2 rounds. We saw the completeness and soundness for these two. We saw that when we have constant number of rounds, k rounds, AMK is equal to AM. So the only public constant round public coin protocols correspond to AM or MA, constant round. So when you have non-constant, let's say n rounds or n squared rounds, it's different. So we can do this replacing MA with AM only for constant many times, not otherwise. Then we saw the proof that AM contains MA. Basically, we boosted the probability of success for probability of success and reduced the probability of error. Completeness and soundness errors were reduced for the MA protocol, and the completeness of MA directly implied the completeness of AM, and the soundness of MA, the boosted soundness, was used to reason the soundness of AM as well. So we could replace MA by AM, and that gives the fact that any constant round protocol proof system boils down to MA or AM. Then we saw this theorem finally that graph isomorphism is NP complete implies sigma 2 is equal to pi 2. So we started with an arbitrary language in sigma 2 which was psi, and then since graph non-isomorphism is co-NP complete, the latter part for all y, this part could be replaced by a graph non-isomorphism instance. And then we use the fact that we saw the 2-round AM protocol. We used that to reason the equivalence between 1 and 2, and 2 is of the pi 2 form. So that implies that an arbitrary language in sigma 2 has a pi 2 characterizations, which proving what we wanted. And that completes what I had for you in this lecture. And there are some more interesting things about public coin protocols which I will present in the next lecture. Thank you.